Swayam Prabha. Digital India. Educated India.
Dear students, welcome back to the organ printing course. So in the last few lectures, we have discussed different types of 3D bioprinting technologies like inkjet bioprinting, extrusion-based bioprinting, and laser-assisted bioprinting. And also we have discussed in great detail about all these different technologies, what are the characteristics or the important features of these technologies, what are the different components of these different bioprinters, and also the advantages and disadvantages of these technologies. And also in the last lecture we have discussed in great detail about the comparison of different 3D bioprinting technologies, like all the in terms of all process parameters, different other characteristics, and also lastly the advantages and disadvantages of all these different technologies. While discussing the disadvantages of all these different techniques, one thing was very clear that these three different techniques, they have a common feature, that is like when we are trying to produce a complex microstructure, then we need to provide support to the complex structure, otherwise we cannot print a very complex structure. Mostly we are able to print a lamellar or a planar structure very well, but whenever there is a hanging geometry or a complex shape is there, then that time that printing technology is not capable enough to print that intricate microstructure or the complex geometry as such. Most of the time, the material, that when we print the material, after printing the material collapse, and or they cannot retain the shape of the structure. That is because in 3D bioprinting mostly we mostly use different types of hydrogels, aqueous based gels, and and also like we have seen that, or we have discussed that we cannot use the very high viscous bio-ink, because if the material is very high viscous, then the cell viability can be an issue. So that's why mostly we use low to moderate viscous bio-ink. So in this lecture we'll discuss a recent development on this bioprinting technology, that is 3D bioprinting in support bath. So we'll see why this last two words, support bath, is important. What is the purpose of this support bath, and how what why we need a support bath basically. Before that, let us again revisit the drawbacks of the conventional bioprinting method. Like we have seen this, like in all this, either it can be inkjet printing, or it can be extrusion based bioprinting, or it can be laser assisted bioprinting. Everywhere the bioprinting is done mostly on the print bed, or it is culture plate or a substrate, right? So where we have a substrate, and then on the substrate we print the material, we print on the substrate, so that the structure can be built on the directly on the tissue culture plate on a petri dish anywhere. But mostly, please note this, that whenever we print this, we print on the stage, so where the support is mostly provided by the print bed or the tissue culture plate, right? We cannot print anything like on air, and mostly the thing will be mostly the layers will attach to the print bed. Okay, so there is, unless we provide any support, we cannot print any structure that is a non-planar structure, or that has some, suppose a pyramid like structure where this part will be hanging. So this part, if unless we provide some support to this hanging geometry, we cannot print a structure like a structure that has complex geometry that has non-planar surface, right? So that is one of the main drawback of this conventional bioprinting method. So due to that, what are the structures if you see in literature with conventional bioprinting method? Mostly they are very simple. They are a very limited complexity of microstructure and 3D anisotomy present in those structures. But to mimic the real native tissue is where the microstructure is very complex. It has a 3D anisotropic structure. Unless we mimic that in our bioprinting method, we cannot achieve that function, that cannot achieve that particular tissue or organ specific functions. So that's why this complexity of microstructure and 3D anisotropy, these are keywords where we need to mimic that tissue in terms of these two properties. And most of the current bioprinted structures are simple lattice structures. Like these are like 090 degree angle. First layer is printed at 0 degree angle, suppose this certain angle, and then the next layer with 90 degree to that preceding layer or any other angle. So basically, we can mostly printed square lattices are being printed with this conventional bioprinted structures. To print a complex structure is very challenging with the conventional bioprinting domain. But these simple lattice structures, they do not recapitulate the microstructure of the native tissue. That means that real microstructure is missing in the conventional bioprinted structures. And if we cannot mimic that structure, we cannot gain the function, or we cannot regain or re-establish the function of that particular tissue structure in a bioprinted construct. So that's why mimicking the microstructure of the native tissue and the anisotomy of the native tissue is very important. So that's why controlling microstructure and anisotropy in 3D is the ultimate goal of all tissue engineering, all bioprinting approaches, so that we can actually mimic the native tissue structure and we can gain the function. So because if we can actually produce a structure produce the tissue with a real microstructure, native tissue mimicking by mimicking microstructure and anisotropy, we will able to reproduce the function of the tissue in that bioprinted structure. If we cannot do that, then it is not possible. So that's why there is this development happened, like started from around 2011, when the first research paper came out on this process, where somebody has 3D printed a structure in a support bath. That means where the bioprinted structure is basically embedded within the support bath. Now we see why basically we need a support bath. As in the last slide, I have discussed that the support is very much required to print a complex geometry. Basically to print a non-planar geometry, support bath is very much required, because most of the time these hydrogels, the biological hydrogels or aqueous based gel, bioink, they are very challenging to 3D print, because the mechanical property or the viscosity of that material is very low, like they are less than 100 kPa. The elastic modulus of those hydrogels are mostly less than 100 kPa. So that's why with this very slow soft soft biological hydrogels, 3D printing is a real challenge. And one way to tackle this is if we can introduce some cross-linking or gelation during the fabrication process, that is in situ gelation during the fabrication process, that is required to maintain the shape and maintain the shape and size of the structure. Okay. Otherwise, what will happen? The structures will deform or collapse after printing the structure. If the hydrogel is very soft, after printing or after the fabrication is done, then they will just collapse or they will deform due to their own body weight, right? So that is the main challenge when printing with very soft hydrogels. So main challenge is to prevent the material from changing shape after placement. So that's what, when you print the structure, suppose when the material comes out through the nozzle or any other means, that time what will happen, we print the material, but the material after some time material starts collapse, and it can deform. So that deformation happen. Because of that, the structural resolution or even the printing fidelity is not that great. So in 3D printing, always there is a challenge to tackle this instability. What is the instability here? The source of main instability in case of bioprinting up with soft jet hydrogel as the, because this hydrogel, they are very soft. They are like a, they are they are like aqueous based, mostly they are aqueous based gels, where surface tension of the material plays a big role. Because surface tension, what surface tension does? Surface tension drives the material. Suppose we printed a line, but if the material has high surface tension, what will happen? That will drive the material towards sphere, because sphere is the low energy state. So surface tension always drives the material towards this low energy state. So that's why if we print a material with high aspect ratio, that will just collapse, and it will probably, we can end up with getting a spheres. Other thing is because of the body forces and due to the gravity driven force, that the, if we suppose if we print a line, or say if suppose if we print a filament or line, a cylindrical line, that collapses because of the gravity driven sag and buckling. So these are the main challenges while printing with support bath. So that's what we need, a support bath to provide support to the printed structures, specifically printed structures with low viscous or low modulus soft hydrogels. These are the few characteristics of this support bath or 3D printing and support bath, that whole concept. Support bath is a, basically support bath, mostly the support bath is made up of some materials that act like a Bingham plastic during the print process. What is a Bingham plastic? Bingham plastic is when the material behaves like a rigid body or solid like structure. Solid structure when there is no shear load, no shear rate, or very less shear stress. Okay, suppose if the material is just kept as such, then the material will not flow. There will be no flow. The material will behave like almost like a solid. If there is no force applied on the material, or if there is a very little force or very little stress applied on the material, but that same material will start flow when the applied shear stress reach a certain level. That means at very low shear rate, the material will not flow. But if I increase the shear rate, shear stress or the force, then the material will start flowing. So that is what a Bingham plastic material like. So because of this, what happens whenever, suppose in case of extrusion based bioprinting, what happens whenever we move, suppose we put the nozzle, we did not, suppose at the beginning we do not put the nozzle inside the support bath, that time the support bath material will be like solid. But when we insert our nozzle of the extrusion bath printing nozzle, when we insert inside the support bath material, what will happen? That time, if we at very low shear rate, again that support bath material will behave like a solid. But when we start moving the nozzle, when we apply some shear stress, and if our shear stress reach that critical stress, just remember critical stress, that is called yield stress, then the material will, the support bath material will start flowing. So it will provide space for this nozzle to flow, right? So that's what happened. So nozzle moves through the bath and the support bath material started to flow. After that, what happened? The extrusion of out of the nozzle and deposition of the hydrogen within the bath. So as soon as, whenever the nozzle moves within the bath, it creates a space within the bath, right? Within the support bath material, and the support bath material just flow because of this, because here the shear stress is more than the critical yield stress. So that time what will happen? The material from the nozzle, the material, the structural material, that or the hydrogel or the bio ink, that will extrude out. We can extrude that material out, and that can be deposited within the support bath structure. Right? Again, when the nozzles nozzle moves away. After that, what will happen? Again, the material, this support bath material, they will again come back to this original position, or they will just encapsulate the print by bioprinted structures, a bioprinted structure or bioprinted that line. Suppose any shape or size, that structure will be, it will encapsulate, and again it will be like a solid structure. So because again it will be like a solid, so it can provide support to the deposited material. So that's what happens in case of 3D printing in support bath. The nozzle, whenever we insert the nozzle, we started moving the nozzle, so the support bath material moves, started to flow. They give space to the nozzle to move, and also give space to the deposited material to come out. And that then again, when the nozzle moves away, then again they come back to the original position, and then they behave like a solid material, and they provide support to the deposited material. So that is what happens in case of 3D printing support bath. Now, after the whole process is done, how can we remove the support bath material? Now, mostly the support bath materials we use, some support material that they can be removed by various ways. One is the one way to remove that. Suppose we use some thermo reversible material. That means that material behaves like a gel, like structure gel, behave like a gel at certain temperature, and above a critical temperature they behave like liquid. So that kind of material we can very well use for this as a support bath material. Also, if the support bath material is also water soluble or soluble in buffer or media, then we can simply wash them in a non-destructive manner, and then that can be very well removed. So this is the whole, in a way, whole concept of 3D printing in support bath. Now this is a this image here, this figure clearly shows you what actually happened. Like suppose here there is a support bath material. In this particular literature they have used gelatin microgel as a support bath material. Now remember, gelatin behaves like a thermoreversible material. As I earlier also I mentioned, it has a critical transition temperature near 30 degrees centigrade. So below 30 it will behave like a gel, above 30 it will behave like a liquid material. So that's what happens here. And another thing is, now gelatin microgel also behave like a Bingham plastic, and Bingham plastic, from this graph you can clearly see any Newtonian fluid where there is no yield stress present in the Newtonian fluid. So here at 0 shear rate, stress also that is stressless. As we increase the shear rate, the shear stress keep on increasing, and it is linearly increasing. So that is the property of the Bingham Newtonian liquid. But in case of Bingham plastic liquid, what happens? You see, at 0 shear rate there is no flow or no shear stress being there. But when the shear stress, at 0 shear stress there is no flow. But when the shear stress increases to a certain value, like till here, no flow of the material is happening. So no shear rate, if you see. But after certain yield shear stress, then it starts flowing. But again, after that, it is almost proportional to the shear stress, and shear rate is proportional, right? Linearly increases. But still, a certain stress value, there is no flow of the material. So that is called yield stress, right? So that's what happening here. Now here, this support bath material, and this is the hydrogel material or biowing that is coming through that is getting extruded through this extrusion by this extrusion based bioprinting nozzle. Then what will happen? Then when the material comes out here, then at the first this needle will be inserted within this support bath, right? And then when the needle moves within this support, at the beginning there is no flow of this support bath material, so it is behaving like a solid, right? But now when I start moving this needle or the nozzle within the support bath, the support bath material, they withstand the flow or withstand the pressure up to a certain level till that yield stress. After that critical value, then when the nozzle moves, then the nozzle can able to move, and the support bath material will also start flowing, and they behave like a liquid like material. So but that liquid material behavior can be visualized or can be present in a localized manner. Whenever this force is being applied, there only the material will start behaving like liquid material. So then the nozzle can flow, and the material, and also that nozzle can deposit the hydrogel material within the support bath. And after this movement is done, like suppose here this thing is getting deposited, right? So after this movement, here again this support bath material again they will come back to the original position, or they will encapsulate the hydrogel material that is getting deposited. Just a minute, let me switch on the. So support bath material, that here it will be getting deposited, and after that nozzle moves away, then it is again the support bath material will come back to this original position, and they will encapsulate the deposited material, and then we can able to, the hydrogel will be very much supported by this support bath, right? That's why these are called support bath. They will support the hydrogel material because at that stage they are behaving like a solid, right? Then so by inserting this nozzle again, just taking out the nozzle one layer up, then putting the next layer. So like this, we can, any kind of structure can be created like this. Here you can see they have created first layer that is printed, second layer another some printed, and the third layer and third or fourth, or simultaneously the whole structure is printed within this support bath material. So this is the beauty of this technique, where it provides support to the hydrogel material, and this hydrogel material is very soft hydrogel. And after this, the release can be done as I mentioned. This gelatin behaves like a thermos reversible material. So above 30, again when you are at 37 degrees centigrade, the gelatin will be liquefied, and then it can be removed easily from these printed structures. And by that time, this printed structure can also get solidified and also get so if we can introduce some cross-linking, some gelation mechanism here, so that the support bath material can also, or sorry, the hydrogel can also get gelated. So this is the main. Now, what are the important properties of this support bath material? This support bath or suspension media, that displays solid-like characteristic in the absence of a applied stress or a very low stresses. Right? So that is the very first thing you should remember. The very first important property of the support bath material, it should not just flow without any applied pressure, or at very low stresses also it should not flow. So they display a solid-like characteristics, and when the shear stress applied at certain above a critical yield shear stress, that is called yield stress. After that, the support bath material starts yielding. That's what the support bath or suspension bath material start yielding. So that means it started to flow. So that's why again any application of shear stress, that can render the material liquid like. Other important property is the self-filling property of this suspension bath or support bath material. That means the support bath microstructure spontaneously recovers after the movement of the nozzle or deposition of the structure. That means when the printing is done, the deposition is done, that time again the support bath microstructure, they will again come back. Okay, come back to their original position, and also, or they will encapsulate the printed structures, and then again they will behave like a solid, and they can provide support to the printed structure. So these are the important properties of support bath. Now in this video, I have two videos to show you what is the important requirement of a support bath. Why 3D bioprinting in support bath is very important for this thing. Now in the first video, you can clearly see when actually we are trying to print with a very soft hydrogel. Like in this case also, we try to print a very soft hydrogel. If you see here clearly, no structure can be getting printed. It's only that because this is very soft material, and due to the surface tension, as I already mentioned, the drop is getting bigger and bigger. So no real structure is present in this case, right? Only the drop is getting bigger and bigger. Due to this, because of the low viscous or low modulus binding, we cannot be able to make a structure. But the same binding, same viscous or same modulus binding, low viscous, same modulus binding, I am printing in a support bath. Suppose this is support bath material and I am printing in a support bath. The support bath is actually providing support to the printed structure. Here this again, they are not coming together as a drop. They maintain the printed the structural fidelity, or the printing fidelity is maintained here. In this case, if you see, they can maintain the shape of the structure, or because in this case, because this material, support bath material, providing support to the printed structure, so that I can able to print a very good structure with the same viscous or same modulus binding. So that's the beauty of this thing. So any kind of complex geometry I can create within the support bath material, and then this support bath material can provide support to the structure, and I can create a very good geometry. So with this thing, we could print a tubular structure with this kind of hydrogel, the soft hydrogel, you can print a tubular structure. So that's the advantage, or that's why this 3D bioprinting in support bath is so powerful, so that we can print very complex geometry also can be printed with this technique, and so that this technique can be very well used. As I already mentioned in the last slide, that the printing complex microstructure, printing 3D anisotropy, printing, all these things are very much possible. And if you see in literature, you will find some examples of using this technology for different applications. Like recently, in last year, there was an important breakthrough where from Israel, Tel Aviv University, some researcher, they have printed a human four-chamber human heart like structure with this, with a hydrogel, with a very soft hydrogel, using this 3D support bath. So using this 3D bioprinting and support bath, they have created a human heart, four-chamber heart like structure, where it has this all the chambers are present, and also the architecture is architecture structure is very similar to the heart tissue. So that's the advantage of using this support bath material. Here also you can see we can create a cylindrical structure. The structure is very much stable. Or the structure is really, the height is more like, it's almost like a 5 to 6 mm height of the structure, or more than that probably. But we could able to make a three-dimensional structures with this thing, with support bath material. Now, what are the different types of support bath materials are available? One important thing is the support bath material should behave like a, it should not be like any other material. It should be behave like a Bingham plastic. That means at very low temperature, that thing, the material should behave like a solid. Low, no, not temperature, low shear stress, the material should behave like a solid, and up beyond a critical or yield stress, the material should behave like a liquid. So these all are the different support bath material that has been used for things like gelatin microgel. People have developed a gelatin. Gelatin is a biopolymer. Now they have, with a special technique, they have created this gelatin microgel. Microgel is mean where this gelatin gel, typically micron size, some tens of microns or less size microns, so like 10 to 50 or maybe some 70 micron, 30 micron microparticles of gelatin microparticle that is suspended in the, or suspended in the, in some, suppose the aqueous buffer, and then so gelatin microgel, so that behaves like, again the behaves like that kind of support bath material that can be all well be used for providing support bath. Again, there are some disadvantages like gelatin microparticles suspended in oxidized alginate. So that is another support bath material people have used. Similarly, silicon nanoparticles also people have used as a similar different suspension of different materials can also be used as a support bath materials. Fluoronics is another support bath material. Fluoronics is another important thing is the fluoronic is a thermoreversible material similar to gelatin. Gelatin is a thermoreversible material. So fluoronic is also a thermoreversible material. So, but the property is opposite to the gelatin. It is below 20 degree it behaves like a liquid. Above 20 it behaves like a gel. So that's why this material is also a very good material for printing the support bath, printing structure, and be is using as a support bath. So the first application of this 3D bioprinting support bath, where the first research group, they have used fluoronic as a support bath material. So in laponite nanoclay, that is also another support bath material can be used. Carbopol is another popular support bath material. So these all are the support bath material that people use for different applications. So that's why that's the, and if you, I encourage you to go through some literatures, and you can find enough examples of this 3D bioprinting in support bath material, and for different applications people have started using, and the application of this technology in different fields, like will also be different 3D complex geometry. People have tried printing like the vascular network. Vascular network is a very complex structure, right? That is very difficult to create with any other conventional bioprinting. But with this 3D printing and support bath, people have actually tried to make this 3D complex geometry, or this vascular network is very much can be printed, and people have shown that it can be printed and it can be used. Similar different applications are there. Please go through the recent literature. I will also share some links for some literatures in the later classes. Thank you very much again for attending this lecture. We'll again meet in the next lecture. Thank you very much.